Today we will start with the module Introduction to Modern Physics. So first in this module we will discuss about electromagnetic waves. It was the great Scottish physicist James Clerk Maxwell who showed that electric and magnetic fields fluctuating together can form a propagating wave, appropriately called an electromagnetic wave. So, a mutually fluctuating electric and magnetic field can form a propagating wave. It was observed by James Clerk Maxwell first, and it is called as electromagnetic wave. Sunlight is a mixture of electromagnetic waves having different wavelengths. Sun is emitting different kinds of electromagnetic waves. Different kinds means having different wavelengths or a spectra of radiations. Each wavelength in the light produces a different color sensation in our eyes, from red to green to violet. The colors are present in the sunlight in the sense that sunlight is a mixture of different wavelengths. Not all radiations are sensitive to our eyes. Only those radiations which is in the region violet to red is sensitive to our eyes, human eyes. So the radiations, the colors from red to violet is visible to human eye. Colors means different wavelengths which are emitted from the suns. So sunlight is a mixture of different wavelengths. An electromagnetic wave in a vacuum consists of mutually perpendicular and oscillating electric and magnetic fields. So the term electromagnetic wave represents mutually perpendicular oscillating electric and magnetic field. So it will have electric and magnetic field which will be oscillating in mutually perpendicular direction. The wave is transverse waves since the fields are perpendicular to the direction in which the wave travels. That means the wave is traveling in one direction, and these electric and magnetic fields are oscillating in two mutually perpendicular direction, and which is again perpendicular to the direction of motion. So it is a transverse wave. It's transverse in nature. All electromagnetic waves, regardless of their frequency, travel through a vacuum at the same speed, that is with the speed of light. So whatever be the frequency or wavelength, all the electromagnetic waves travel through a vacuum at the same speed. The speed of light is 3 into 10 to the power 8 meter per second. The frequency which is represented here by letter F and the wavelength lambda of an electromagnetic wave in a vacuum are related to its speed through the relation C is equal to F lambda. The wave speed of an electromagnetic wave in a dielectric medium is given by V is equal to 1 by square root of mu 0 epsilon 0, where mu 0 and epsilon 0 are permeability and permittivity of the dielectric respectively. So the speed of an electromagnetic wave is represented by the relation V is equal to 1 by square root of mu 0 epsilon 0. Where mu 0 and epsilon 0 are the permeability and permittivity of the free space respectively. Electromagnetic waves cannot propagate within a conductor. They are totally reflected when they strike a conducting surface. So this kind of waves cannot travel through a conductor. Whenever it strikes a conductor, it is deflected or reflected from this conducting surface. And the representation of an electromagnetic wave is shown here. Here, this is the direction of propagation, this x direction, and one field, that is the electric field, is oscillating in the y direction, and the magnetic field is fluctuating in this plane, in this direction, this horizontal plane. So these two are mutually perpendicular direction. This electric and magnetic field are in, that is this one is in this direction and this in this direction. So these two are mutually perpendicular, and these two are together perpendicular to this propagation direction. So this is a electromagnetic wave. And in an electromagnetic wave, the electric and magnetic fields are always perpendicular to each other. So the right hand rule applied to electromagnetic wave. An electromagnetic wave propagating in the positive x direction, E and B are perpendicular to each other in phase. The direction of propagation is given by the thumb of the right hand after pointing the fingers in the direction of E and curling them towards B. So this is the right hand rule. What does it mean? We have shown here the figure of electromagnetic wave. So this is the direction of propagation. So the direction of propagation is in the is shown by the thumb by and direction of propagation is given by the thumb of the right hand after pointing the fingers in the direction of E and curling them toward B. Okay, so you can just hold your hands like this. That is, if this is the thumb, this is the direction of propagation, and when we are curling your fingers, the fingers tips will represent the direction of E, and the curling direction, will represent the direction of magnetic field. So all these will be in mutually perpendicular direction. This is the right hand rule applied to the electromagnetic wave. Now, what are the properties of electromagnetic waves? In brief, we can say these are transverse waves in nature. And the second point is the waves propagate through space with the speed of light, that is with 3 into 10 to the power 8 meter per second speed. And the speed of the electromagnetic wave can be given by the equation C is equal to 1 by square root of mu 0 epsilon 0, where mu 0 and epsilon 0 are permittivity and permeability of free space. The rate of flow of energy in an electromagnetic wave is described by the vector S called the Poynting vector, which is defined by the expression as 1 by mu 0 E into B. That is, when a electromagnetic wave is propagating through a medium, the rate of flow of energy is represented by the vector S, which is known as the Poynting vector, which will be the product of this electric field and magnetic field vector divided by mu 0. And the SI unit of this quantity is watt per meter square, because this is the energy rate. And another point is its magnitude as is related to the rate at which energy is transported by a wave across unit area at any instant. So the quantity S related to the rate at which energy is transported by wave by the electromagnetic wave across a unit area. The energy in electromagnetic wave is divided equally between electric and magnetic field vectors. So electromagnetic wave consists of electric and magnetic field. So the energy is divided between these two fields, electric and magnetic field. Electric vector is responsible for the optical effects of an electromagnetic wave. Electric vector is the reason for the optical properties of electromagnetic waves. The intensity of electromagnetic wave is defined as the energy crossing per unit area per unit time, perpendicular to the direction of propagation of electromagnetic wave. It is the usual definition of intensity. It is the energy per unit area per unit time propagated or transported by the electromagnetic wave when it is propagating. So these are about electromagnetic wave and its characteristics. Now what is electromagnetic spectrum? You know what is a spectrum? So it's an arrangement of or array of electromagnetic radiations in the sequence of their wavelength or frequency. So this is known as electromagnetic spectrum. So the electromagnetic spectrum of sun is given by given in this figure. Here is shown the wavelength, and the upper axis shown frequency, and in the increasing order of frequency, these are in the order radio wave, microwave, infrared, and this band represents the visible region, and this is ultraviolet, this is X-rays and gamma rays. So the visible portion of the spectrum is relatively narrow. The boundaries between various bands of the spectrum are not sharp here, but instead are somewhat arbitrary. So here we have shown here the spectrum model, and the boundaries shown here are not fixed, or this can there may have slight changes. There are a lot of different types of electromagnetic waves. They differ only by their frequency or wavelength. They are named according to their frequency or wavelength. So this is our electromagnetic spectrum of sun, and there can be any kind of radiations with different frequency or wavelength, and they are named according to their frequency or wavelength. So this is about electromagnetic spectrum. So we have seen what is electromagnetic wave and its characteristics, and now we discussed about the electromagnetic spectrum. So the next topic is black body radiation. So this is one experimental phenomenon that could not be adequately explained by classical physics. So black body radiation was one of the phenomena which classical physics couldn't explain properly. So all normal matter at temperatures above absolute zero emits electromagnetic radiations, which represents a conversion of a body's internal thermal energy into electromagnetic energy, and is therefore called thermal radiation. So what happens when a body heats or its temperature rises from a normal temperature, normal room temperature? What happens is the body absorbs heat energy, or its internal energy increases, or its internal thermal energy increases, and this energy is being converted into electromagnetic energy, and this electromagnetic energy is emitted as radiation. This is what happens when a body is heated above absolute zero. So conversely, we can say all normal matter absorbs electromagnetic radiation to some degree. An object that absorbs all radiations falling on it at all wavelengths is called a black body. So a black body can be defined as a body which emits all kinds of radiations falling on it at all wavelengths. When a black body is at a uniform temperature, its emission has a characteristic frequency distribution that depends on the temperature. This emission is called black body radiation. So what happens when its temperature is increasing? When a black body is at a uniform temperature, suppose the body which absorbs all radiations at all wavelength, which is called a black body, is at uniform temperature. Its emission has a characteristic frequency distribution, and this characteristic distribution of frequency radiation is depending on the temperature of this body. This emission is called black body radiation. A room temperature black body appears black as most of the energy it radiates is infrared and cannot be perceived by the human eye. So a black body at room temperature appears black because it emits infrared radiation and which cannot be sensitized by a human eye. That's why it appears black. Because the human eye cannot perceive light waves at lower frequencies, a black body viewed in the dark at the lowest, just faintly temperature, subjectively appears grey even though its objective physical spectrum peaks in the infrared range. When it becomes a little hotter, it appears dull red. As its temperature increases further, it becomes yellow, white, and ultimately blue-violet. So you might have seen when an iron rod is heated, its color is changing. Its color is changing from red, white, or when it is very hot, it becomes blue-white. So this is the case of iron rod when it is heat above the room temperature. And we cannot detect any other radiations above this wavelength or frequency. That's what the case of black body also. When it is emitted in the infrared region, we cannot detect this radiation and the body appears as black. Okay. So black body radiation has a characteristic continuous frequency spectrum that experimentally depends only on the body's temperature. More precisely, a body emits radiation at a given temperature and frequency exactly as well as it absorbs the same radiation. So, a black body radiation will have a characteristic frequency spectrum, a continuous spectrum that experimentally depends on the body's temperature and that depends on the temperature of the body. As the temperature varies, this frequency or the wavelength of the emitted radiations vary, and which will give you the spectrum of radiation. Okay. More precisely, we can say a body emits radiation at a given temperature and frequency, exactly as well as it's absorbed. So a body emits radiation exactly as it absorbs the radiation. So any body at any temperature above absolute zero will radiate to some extent. The intensity and frequency distribution of the radiation depends on the detailed structure of the body. To begin analyzing heat radiation, we need to specify about the body doing the radiating. The simplest possible case is an idealized body which is a perfect absorber and therefore also a perfect emitter. Sorry. So the question is how a black body can be modeled. So in 1859, Kirchhoff had a good idea like a small hole in the side of a larger box is an excellent absorber. So how can we create a black body? That is a body which absorbs all radiations at a wavelength and emits just like its radiation as it's absorbed. So here Kirchhoff made this idea of a large box with a small hole in the side of this box. So what happens? Any radiation that goes through the hole bounces around inside this box. So and we are passing radiation inside this box through this hole which we had made on the sides of this box. So what will happen? The radiations will go inside and bounces inside this box. And what happens when it bounces inside this box? A lot getting absorbed in each bounce and has little chance of ever getting out again. So there is only a single hole at the sides. So when it is centering the hole, it bounces inside this box, and each bounce they will get absorbed, and the chance of getting out of this and the chances of getting this radiation out of this box is very low. So this is can be this can be a representation of a perfect black body. By the 1980s, experimental techniques had improved sufficiently that it was possible to make fairly precise measurement of energy distribution of black body radiation. So the techniques have improved by 1980s, and we could measure the energy distribution of black body radiations. In 1995, the University of Berlin, Wien and Lermer in the experiment found a radiation intensity frequency curve as in figure. I have to check that this is 1985, I think. By measuring the black body emission curves at different temperatures, they were able to construct two important phenomenological laws: Stefan-Boltzmann law and Wien's displacement law. So this is the Wien and Lermer experiments curve. That is, this is the black body radiation curve they measured in their experiments, and from their observations of black body radiations with a different temperature or different temperatures curve, they deduced two laws: Stefan-Boltzmann law and Wien's displacement law. So what are these laws? Here, look at this figure. This is lambda, wavelength of emission, and this is the spectral energy distribution. So the temperature is varied. Each curve represents different temperature, and the peak of this energy distribution varies as the temperature increases, and the peak is also shifting from the wavelength region. So this is shifting to left. Okay, these are not peaking at the same wavelength for different temperatures. Okay, so these are the observation. So what are Stefan-Boltzmann law and Wien's displacement law? The first quantitative conjecture made based on the experimental observation was the Stefan-Boltzmann law, 1879, which states that the total power radiated from 1 square meter of black surface goes as the fourth power of absolute temperature, which would say the Stefan-Boltzmann law states that the total power radiated per one square meter of a black body surface can be represented as equal to the fourth power of the temperature. That is, P is the power, and which is proportional to the fourth power of temperature, and the proportionality constant can be equated with this proportionality constant sigma. So here P represents the total amount of radiation per square meter, and sigma is a constant called Stefan-Boltzmann constant, which have a value 5.67 into 10 to the power minus 8 watts per meter square per Kelvin raised to 4. T is the absolute temperature. So this is Stefan-Boltzmann law. So the power is proportional to the fourth power of absolute temperature. What is Wien's displacement law? Wien's law identifies the dominant wavelength or peak wavelength or the color of light coming from the body at a given temperature. In fact, the frequency is directly proportional to the temperature. Nu max, this is frequency which is represented by the nu. Max means the maximum frequency at which the peak of emission appears is proportional to T. This represents the Wien's displacement law. So this Wien's displacement law tells us about the relation between the maximum frequency or the peak frequency of radiation with the absolute temperature. They are, if we are representing this in terms of frequency, they are directly proportional. We can represent this in terms of wavelength also. If we are representing this in terms of wavelength, then it will be inversely proportional. So here the proportionality constant in frequency, if we are expressing this in terms of frequency, the proportionality constant is 5.879 into 10 to the power 10 Hertz per Kelvin. As we already know, when an iron is heated in a fire, the first visible radiation, which will be around 900 Kelvin, is deep red, the lowest frequency visible light, which is the lowest frequency visible light. Further increase in T causes the color to change to orange, then yellow, and finally blue at very high temperature, which is usually about 10,000 Kelvin or more, for which the peak in radiation intensity has moved beyond the visible into UV. What does this mean? That is, as the temperature increases, the frequency of radiations also increases. Okay, that's what is clear when we are heating an iron body in fire. So that is in agreement with this relation, nu max proportional to T. This is the Wien's displacement law. We can represent this in terms of wavelength. If it is the temperature is directly proportional to wavelength, frequency, then the temperature will be inversely proportional to its wavelength. So this rule can be, or the Wien's displacement law can be represented in terms of wavelength as lambda max is equal to B by T, where the wavelength and the temperature are inversely proportional. And this is the proportionality constant. So in terms of the wavelength unit, the proportionality constant is 2.89 into 10 to the power minus 3 millikelvin. Or more convenient to obtain the wavelength in micrometer, we can represent it as approximately 2900 micrometer Kelvin. This is an inverse relationship between the wavelength and temperature. So the higher the temperature, the shorter or smaller the wavelength of the thermal radiation. That's what this law says. That is, when the temperature is increased more and more, the wavelength of the peak emission will be shorter and shorter. The lower the temperature, the longer or larger will be the wavelength of thermal radiation. So for visible radiation, hot objects emit bluer light than cool objects. That's clear from this, very clear from this law. So for visible radiation, hot objects emit bluer light than cool objects. Okay, hot object means temperature is high, so it will emit more higher frequency radiations. Okay. Now, remember, the thermal radiation always spans a wide range of wavelengths as shown in our previous graph. This graph. Okay. A wide range of wavelengths as shown in figure. And the above equation, that is the relation between wavelength and temperature, specify the single wavelength, that is the peak of the spectrum. So, although the sun appears yellowish white, when you disperse sunlight with a prism, you see radiation with all colors of the rainbow. Yellow just represents a characteristic wavelength of the emission. So the yellowish light of sun represents only characteristics wavelength of the emission, but when it is dispersed through the prism, we can see the different wavelength of the sunlight. Okay, so this law says only about the peak wavelength. That doesn't mean that it contains only this wavelength. It covers a spectrum of wavelength, and the peak of this wavelength of radiation is at the can be represented by this temperature wavelength relation. That's what we described here. Now associated with this, we have to discuss one more term, that is ultraviolet catastrophe. So the classical, during the 19th century, much attention was given to the study of heat properties of various objects. An idealized model that was considered as a black body. So the 19th century the heat properties studies had much importance in various objects. An idealized model that was considered was a black body. We can think of the radiating energy as standing waves inside our black body cavity. So we have discussed how a black body is modeled in laboratory. That is a large box with a small holes at the side of this box. So we can think of the radiating energy as a standing waves inside. That means the radiating energy can be modeled by a standing wave which produced inside the black body. That is, imagine this is a large box, and suppose here is a hole, and when the radiation is coming out, it will continuously bounces here and there, and at each bounces energy will be absorbed by the body, and the chances of getting out of this body is very poor. And so it can be modeled as a black body. That's the case. So the energy produced can be the radiating energy can be modeled as a standing wave inside this black body. The energy of the radiating waves at a given frequency nu should be proportional to the number of modes at this frequency. So if we are imagining standing waves as the radiating energy as standing waves inside this cavity, the energy of the radiating waves at a given frequency nu should be proportional to the number of modes at this frequency. So the energy is proportional to its number of modes of frequency. Means how many modes of vibrations are possible. This is a single mode of vibration, second mode of vibration, third mode of vibration, etc. So how many modes of vibrations are possible inside the cavity. So classical physics states that all these modes have the same energy kT. So classically all these kinds of energy will have same energy, which is equal to kT, and as the number of modes is proportional to nu square. So the energy can be represented by E proportional to nu square into kT. So the energy can be represented as E is E proportional to nu square kT. That is, each modes of energy have same energy, and it is proportional to the frequency. this is a proportionality constant not equal to sign. So there may have another terms in this energy expression. So we are representing this equation in order to represent the proportionality of this frequency terms with the energy. So this implies that we would expect most of the energy at a higher frequency, and this energy diverges with the frequency. So what this equation tells us about tells us that as the frequency increases, the energy also increases, since E is varying as V square. So when the frequency becomes larger and larger, the energy diverges. In the limit of infinitely high frequencies, when the frequency becomes infinitely large, the energy should also go to infinity. So according to this equation, when the frequency goes infinity, the energy also should go infinity. But in reality, what happens is that the energy density falls to zero as frequency tending to infinity. So this is clear from this picture. So this is the energy distribution graph. You can see from from this figure that this is the wavelength and this is the energy distribution. So as the frequency, this is the increasing order of wavelength. So this will be the increasing order of frequency. So as the frequency goes higher and higher, the energy falls to zero. So that's what we are experimentally seen, or so that's what we are seen experimentally. So this is a discrepancy, but theoretically what happens when frequency goes infinitely large, energy should go infinitely large, but experimentally or observationally we could see that the energy falls to zero when frequency tending to infinity. This discrepancy is known as ultraviolet catastrophe. So this is the ultraviolet catastrophe. That is, theoretically the energy emitted by the black body radiation is go to infinity or increases with the frequency, and it should go infinitely large when frequency goes infinitely large, but actually the energy falls to zero when the frequency tending to infinity. So there is a discrepancy or paradox, and this discrepancy is known as ultraviolet catastrophe. It was left to Max Planck to resolve this gripping paradox, but postulated that the energy of the modes could only come in discrete packets or quanta of energy. So the Max Planck reduced this or solved this paradox by assuming that the energy is the modes of vibration is quantized, which can be represented as is equal to h nu, 2h nu, 3h nu, etc. So the difference between each energy level is h nu. So using statistical mechanics, Planck found that the modes at higher frequencies were less likely excited, so that average energy of these molecules would decrease with the frequency. The exact expression for the average energy of each mode is given by the Planck distribution. So Planck defined a distribution function using the statistical mechanics equation. And so the energy distribution function he defined as h nu by exponential of h nu minus kT. This is according to the MB statistics or Maxwell-Boltzmann statistics equation. So the energy density can be represented by this equation. So this is the modification which is made by Max Planck And we can see that if the frequency is low means this term, the exponential term h nu by kt, this exponential factor is very low here. Then the average energy tend towards the classical results, and what happens, this will tending to a negligible value, so the result will converge to the classical energy value h nu. We get the average energy classical result. And as frequency goes to infinity, what happens when frequency go to infinity means this term will becomes very dominant and this energy goes to 0. So this is just as what we have observed, or what we are expecting from this measurement. That is, our measurement result is that energy tending to 0 when frequency tending to infinity. Okay, so it is this equation satisfies this condition. That is, according to this equation, and the frequency goes to infinity, this term becomes denominator term becomes infinite, because this is in the numerator, so the exponential factor become very high, and so this tending to 0. So frequency tending to infinity means energy tending to 0 here. So by modifying the energy equation using the MB statistics by Max Planck, we could solve the ultraviolet catastrophe. So Max Planck was the first person to properly explain this experimental data. Rayleigh and Jean made the assumption that energy is continuous, but Planck took a slightly different approach. He said energy must come in unit interval instead of being any random unit or number. He instead quantized energy in the form of E is equal to nh nu, where n is an integer, h is a constant, and nu is a frequency. So in the Max Planck, so in the previous situation, the previous case, the situation was the energy was assumed to be continuous energy of standing waves. So Max Planck made the modification that he said that energy must be quantized, or it must be come out in intervals with some quantized quantity or with some unit, and he specified this energy as nh nu, where h is the Planck's constant, nu is the frequency, and thus he could solve this paradox or this catastrophe. This assumption proved to be the missing piece of the puzzle, and Planck derived an expression which could explain the experimental data. So Max Planck solved this ultraviolet catastrophe by making the assumption that energy is not continuous but is discrete or quantized. So that's how this ultraviolet catastrophe is solved. So the energy density distribution, final energy distribution is obtained like this, which will satisfy our experimental data of energy distribution. So this equation can take different forms in different textbook. This is just for your knowledge. So this equation is known as Planck's distribution law for black body radiation. Here h is the Planck's constant, and which will have a value 6.625 10 to the power minus 34 joules second, which is known as Planck's constant. So this is about ultraviolet catastrophe, which is solved by Max Planck. So we have discussed in this class about electromagnetic spectrum or electromagnetic wave, black body radiation, and two laws associated with this, that are Stefan-Boltzmann law and Wien's displacement law, and finally the ultraviolet catastrophe and how Max Planck solved this catastrophe. Okay.